Okay, so we left off on Friday with taking some notes on C4 spreading. You should be taking a quiz on Monday on C4 spreading, which is on Classroom. And then after this, we're kind of getting into what is now the full-blown theory on how the Earth's surface changes over time. So we started off with continental drift. That's when Alfred Wegener said, hey, these things look like they fit together. There's some fossils that line up. There's climates that are weird for where they're found now on the Earth's surface. But he didn't really know how those continents could move around. So then they found mid-ocean ridges. They saw that there were patterns, symmetrical patterns of the magnetic reversals on both sides of this ridge. They saw that the new rocks were in the middle, the old rocks were on the outside. And the only explanation for that is that these ocean ridges were moving away from each other. And the new rock was forming in the middle, and it pushed all the older stuff out to the outside. But that kind of left a big question still that really hadn't been answered fully. If the ocean is always getting bigger at these ridges, why isn't the Earth getting bigger overall then too? Because that's, or where is the extra crust going? Like when it moves over here, is there just a place where it all piles up? Is the Earth getting bigger in general, or is there a place that this goes? So that's kind of where plate tectonics comes in. They noticed that there were different plates on the Earth's crust. So it's a theory where Earth is made up of tectonic plates that move together. They can move away from each other like the seafloor, or they can move past each other. So those are kind of our three options here, the three ways that a plate can move compared to another plate. And we're going to have a little bit fancier names for each one of these motions in a little bit here. But otherwise, what tectonic plates are is they are chunks of the lithosphere. So they're the outer solid cool layer of the Earth that is broken into many plates. You could say pieces if you didn't want to use the same word as the definition. Okay, and then we've got another important part of this whole theory here is the asthenosphere. So this is going back to our layers of the Earth that we started off with. This is the plastic layer, or the kind of gooey layer. It's semi-solid, semi-liquid. The plates can slide across it. The magma that makes up this layer can move, and it can create these convection currents. So if we go back to our thermodynamics cup project, you can have, the hot stuff rises, and then it's going to push on the plate when it gets to the top, and then it cools down, and you have these convection currents that go on in the asthenosphere, which is important for how it's moving. So that brings us to close to our last page of notes here. So we have a couple things going on here. We have three different types of plate boundaries. So the first type is divergent, second type is transform, third type is convergent. So the definition for divergent is two plates moving away from each other. So diverging, if two lines diverge, they go away from each other. So plates that diverge are moving away from each other as well. So this would be like a mid-ocean ridge. They're moving away. On transform boundaries, two plates slide past each other. So that's also known as a fault. Probably the best example of where one of these is the San Andreas Fault in California. And then we have convergence. So this is where two plates crash into each other. We can have actually several different versions of this one, and we'll see pictures down below. But when we have different types of plates collide, different things can happen. Right. So where we find these, the location. So the mid-ocean ridge, the mid-Atlantic ridge is an example of a divergent. And I think I've mentioned in a couple classes that the Horn of Africa, like on the continent, it looks like it has a little rhino horn on one part of it. That actually has something in it called the Great Rift Valley, and that part of Africa is actually getting pulled away from each other. So, in theory, there might be an ocean now in several million years where this Great Rift Valley is if it continues to spread apart. I mentioned location is San Andreas Fault in California, and the convergent is, if you've ever heard of the Pacific Ring of Fire, pretty much all the way around the Pacific Ocean is a convergent boundary. And then since India is slamming into Asia, Himalayan mountains are actually the result of the convergent boundary there. Okay, so we could look up some videos, I guess, of some of these. Not videos, but pictures. So San Andreas Fault. Look up that. It's this huge line down California. The map of it, I guess, is right here. Goes for quite a lot of miles. It looks like this weird little ridge going down here, like it's got two plates. So if you're standing on one side, you're standing on like the North American plate. If you're standing on the other side, you might be part of the Pacific plate. I didn't have to look into that one, but anyway, these two plates are one's gonna slide up while the other one slides the opposite way. They slide past each other, just like the arrows show on here. So this obviously creates a lot of earthquake issues in California. And technically, the people that say that California is going to slide off into the ocean don't really know the way that these plates move, because California isn't going to break apart. It's just going to continue to slide up along California's coast. You're not going to just have California suddenly jump off and have a big piece in the ocean. Okay. So what was the other one? The Rift Valley. Let's see if there's any decent pictures of those. So here's the Horn of Africa. We've got this chunk right here, the East African Rift or the Great Rift Valley. This whole chunk of Africa here is actually getting split apart from the mainland. So this chunk is moving out into the sea. This chunk is moving the opposite way. So we might actually have part of the ocean, if it gets spread thin enough, fill in right here. And you might actually end up with another island, kind of like how Madagascar's formed there. Okay. And otherwise, if you just look at it, it pretty much just looks like a valley. You wouldn't know anything different, but those two plates are actually moving away from each other. Okay. So that's the location where these different boundaries are found. What they form, or what can happen at this place. It'll form mid-ocean ridges, it'll form rift valleys. There's some other things that we could talk about happening here. You're going to have earthquakes that happen. Okay. The big thing at a transform boundary is you're going to have faults that form. This is where just rocks slide past each other. You're going to have earthquakes that happen at this boundary too. Oops, that's not good. Okay. And then the other one here, you can call these a subduction zone. So this is where the oceanic crust moves under the continental crust. And this was the big missing piece from seafloor spreading. This is what happens to the older crust on the Earth, is it actually moves underneath. I'll show the pictures probably at this point. It moves underneath and gets melted again. So we notice that this oceanic crust goes underneath and it goes into the asthenosphere and then it melts. So that's what happens to the old crust. And we call that a subduction zone. Subducts means just goes under. So the oceanic crust moves under the continental crust. Or if you have two ocean crust pieces meeting each other, the older, cooler, and therefore more dense crust goes underneath the ocean, or goes under into the asthenosphere. So the older it is, the cooler that crust is, the more dense it is, means that it's going to be the one that goes under and melts. So continental crust is made up of different minerals and different rocks than oceanic crust. And those minerals and rocks are a little bit less dense than oceanic crust. So that's why it's always the ocean that goes under when you have continental hitting oceanic. The oceanic is always more dense than the continent, so the ocean goes under. If you've got two pieces of continental crust hitting each other, they're roughly the same density. So you just have areas of uplift, they call it, where mountains are formed. So this is why the Himalayan mountains are being created. We have India smashing into Asia, which are both continental crusts, and it makes some of the tallest mountains in the world. Okay. Now I didn't have a picture of two oceanic crusts meeting each other, but I guess I could possibly do that here. Oops. Okay, so the first one might have been the best, but I'm not seeing really what I was hoping to see yet. Here we go. That'll do it. So we see here's oceanic crust. Here's another piece of oceanic crust. What I know is true is this crust that's going under is older and cooler than the crust that is on top of it. And what we also notice here, and I even had it in our note pictures a little bit too, is wherever you have a subduction zone, the water that's kind of in the rock and the sediment from the ocean makes it easier for that rock to melt. And if it melts, it creates these magma areas. So wherever you have a subduction zone, you actually have volcanoes happen as well. So we've got a little ring or string of island, they call them volcanic island arcs. We've got volcanoes on like the west coast of the United States, like Mount St. Helens and things like that. That's because there's a plate sliding underneath the western part of the United States, like under Oregon and Washington. So those mountains are volcanic occasionally. Right. So you can have an uplift zone, which means mountains are made. So if we were gonna put some things here that also form, you can have earthquakes. These earthquakes tend to be deeper. They can be deeper because if the plate that's sliding under suddenly cracks and snaps off way underneath in the asthenosphere, you're going to have a deeper earthquake. You can form mountains here because of the uplift, and you can have volcanoes form at this one too. Okay, these tend to be the more explosive volcanoes, the more violent, the ones that you're going to hear about on the news. And I guess something to add here is like a mid-ocean ridge has obviously got volcanoes on it too, but you don't really hear too much about those ones, probably partly because they're under the ocean, also because they're not as violent of an explosion or an eruption, I guess. Okay. So those are some of the things that form here or happen here. Notice we have earthquakes happen at all of the plate boundaries. Volcanoes happen at 2 of the 3. The deeper earthquakes will happen at the subduction zone. The earthquakes that happen at the mid-ocean ridge tend to be a lot weaker, and they don't They aren't going to like cause tsunamis, or you're probably not even going to hear about them on the news because they're in the middle of the ocean and they don't really affect much. It's the earthquakes that happen at a fault or on a subduction zone, like on the west coast of the United States, whether you're in Alaska or California. Those are the bigger ones and the ones we hear about. Okay, very simple drawing. Two boxes, arrows moving away for divergent. Two boxes, they slide past each other. They don't go into each other, they don't go away from each other, they slide past for transform boundary. And then convergent boundary is where the two plates meet each other. Now, this is a very simple drawing. What I'm gonna want on the quiz though is a little bit more like it looks on the actual Earth's surface. The worksheet that's coming up where you have to draw these different boundaries, I'm gonna want a little bit more realistic looking ones, meaning, you know, it's not just a flat box. You can show the mid-ocean ridge. You can show the arrows on the crust there. You can show the volcanoes being made. You can show mountains being made. You can show that a road or a river kind of gets shifted over. You can show a little bit more detail on the worksheet and the quiz. That's what I'm expecting, I guess. Okay. So those are the three plate boundaries. We've got divergent, transform, convergent, moves away, slides past, moves together. And the only other thing here is kind of evidence of plate movements, of plate tectonics. So now that we have GPS, we can actually see these plates move, so we can track them. So GPS has allowed us to track the position of each plate every year. Some of them move faster than 5 centimeters a year, some of them move slower, but I guess a good middle ground or average is, this little squiggly means approximately 5 centimeters a year. All right, so very slow. It would, at 5 centimeters a year, I don't know, 5 centimeters, 2 miles. So that really ridiculously small number. Calculator. I guess it won't paste. I was just trying to figure out how many years it would take to travel a mile at 5 centimeters a year. My guess is quite a few. The other evidence we have for plate tectonics is obviously earthquakes and volcanoes happen at these boundaries. So if you look at the place where earthquakes and volcanoes happen, you're going to notice that they kind of create this map of the plate boundaries for you. You can find out where the plate boundaries are just by looking at the epicenters of earthquakes or where volcanoes are found on the Earth's crust. There's exceptions, like earthquakes happen for some reason in Missouri occasionally. They're not huge ones, but there is a area that's geologically active where earthquakes happen, small ones, in Missouri, and it has nowhere close to a plate boundary. Or there's volcanoes in Hawaii. Hawaii isn't by a plate boundary, but there's a hot spot that created those volcanoes. So there's other things that can create these, but if you look at where the majority of earthquakes happen, or the majority of volcanoes, it will create these plate boundaries for you. And that's actually one of our worksheet activities that we're doing this week, is looking at earthquake and volcano locations and trying to find out where the plates are themselves. Okay, so what causes plate movement then? There's three main things that can actually help move a plate. We can have what's called ridge push. So the oceanic ridges can push the plates. So gravity pulls down on the crust, the mid-ocean ridge. So you want to remember that like the mid-ocean ridge is a mountain chain and it kind of has this upward slant. So that creates part of the crust that's higher. So if it's higher, gravity is going to help pull it down. Slab pull is the plate that sinks into the subduction zone. Since it's going down, it's going to be lower, and gravity will pull it. And then we have the convection currents I mentioned earlier in the video. So the warm magma rises, the cool magma sinks, and when it's in between, it's going to create a current that's kind of slides under the plates and pulls them. So what I have here is some different plate boundaries. So here we have our divergent, it's our mid-ocean ridge. The plates move away from each other. And why I have these arrows here this time though is because of reason number one. So ridge push. Ridge push is shown by that number one here. So because they're higher, it pushes down and gravity helps the continents move, the plates move. Then over on the convergent boundary here, we have a subduction zone, we have a trench. That's the other thing I forgot to put on the notes for what can happen at a convergent boundary. You can have a trench. So a very deep part of the ocean, because of kind of going underneath the continental crust, it makes a very deep section of the ocean. This is the deepest places you could go, like the Marianas Trench. So number two is what, slab pull? Yes, slab pull, where this plate goes into the crust, it's pulling it down, it's helping move it. But then one of the big ones is convection currents. So magma rises up here by the ocean ridge. Some of it goes up and makes new crust, but a good chunk of it takes a bend here, and when it's going right underneath the crust, when it's moving this way, it's kind of pulling it from friction and helping that crust move. And then it'll cool off, it'll sink, and it'll start the whole process over. So these are the convection currents. Okay. So that's the only other thing that I think we should go back and do. I forgot about trenches, which happen here too. So volcanoes happen, trenches are formed. Here though, so we can still see it. Okay. So some of the questions on the quiz have you try to figure out like what boundary does a volcano happen at? What boundary would you find a trench? Which boundary would you find a mid-ocean ridge? Which boundary would you find a fault at? So it's not always just knowing what ways they move, which is another part of this, but it's knowing like what features, what things happen at those boundaries too. Okay. Part of it is being able to draw them in the slightly fancier way. I might show you the unfancy way and ask you which type of boundary that is. But if I ask you to draw it, I want you to draw it in a fancier way. And when you get to my answer key, I even put in some of like the convection currents that move it. I definitely show volcanoes if they happen. I show trenches if they happen. I show a fault or label it. I label ocean ridges. Just try to do a decent drawing of the way that it looks. I show arrows to show the movement, and I label some of the features that I find. So that's going to help you have a really good drawing, but not only have a good drawing, but be able to know what happens at that zone, what you find there, and what causes things to move. So if you want to know what way the convection current goes, you just got to know what way the crust is going to move. So at an ocean ridge, it moves this way, so I draw my arrow for the convection current going that way. I draw it going this way because this crust moves that way too. Okay. Otherwise, those are the notes. You can obviously watch this however many times you need to. You could have paused it all along the way so you had time to write. Any of those things that come along with an online class. If you have questions, feel free to email me at kellerj@prairiehill.org. I'm going to try to have Guardian up so you can chat with me throughout the school day. I tested it out yesterday. I think it's going to work when I have all my classes open. So otherwise, good luck.